Well, welcome to the August edition of the Forge Modeling and Simulation Community Meeting. Once again, as the last month, this meeting will be somewhat dominated by the Forge modeling team. We'll go through some information, have some open questions back and forth, and then as we I'm thinking probably with the next month or thereabouts, we'll start inviting the community to come back in and give some more information. So without further ado, if my screen will let me. So then the agenda, I want to briefly talk again about some data availability. And then we'll have a presentation overview of the microseismic data measured and modeled. Our Peng Zhu Jing from Itasca will give us that presentation. I'm sorry, Gosha, I see your meeting about presenting. Okay, never mind. And also we'll talk about some initial planning for the location and completion of well 16B. We're going to take that a little bit further than what we did last time. So I don't want to spend too much time speaking myself. Once again, we just for the data availability from the recent stimulation, pressures and flow rates, as I said last time, those are available on the GDR now. Big news is in the last month since our last meeting, we do have a catalog of the microseismic data, and I should say data being post-processed. That still is probably somewhat going on, but we do have a catalog on GDR available now. We'll talk more about that as we go. Water samples and tracer data, that still is in process. And so we will, as soon as I get more information on that, I will post it here. And strain data, we did get some preliminary data for some of the surface strain measurements. That data is somewhat being reprocessed. We hope to have the final versions of that here soon. But we'll go from there. So once again, keep your eyes as things get really, as big data sets get dropped, the Forge communication team normally will do a post to their social media channels. Keep your eyes open for that, and we'll go from there. So now some of the exciting stuff. This is, I'm going to show some plots of the microseismic hypocenters of the catalog that we have available right now, thanks to our friends from Geoenergy Suisse, who did a lot of that processing in our seismic team, Chris Pankow, Ben Dyer. My slides are moving on their own without me touching them. So shown here is essentially in this darker blue is the actual trajectory of well 16A with depth in meters shown on it. Shown here in red is for right now what we're calling our planned well. That is well 16B, and for right now, what it's essentially going to do, and this has come off from some meetings that we had with the stat and with others, is that the initial design right now is it will parallel 16A and be directly above. How far above is to be determined, and how be the final completion the details are still also to be determined. So, but that's just there for scale. So this red line here is right now 100 meters above the blue. And here are our microseismic events from the first 3 stimulations that happened in April. Zooming in a little bit more, so what you're seeing here is essentially a slice on an azimuth of 15 degrees. Once again, blue is well 16A. These white intervals are the open intervals. So the first stage of stimulation happened in the toe, is about 200 feet. And I apologize, I'm mixing units between feet and meters. But I'm going to keep doing that out of convenience. Our first perforated stage is here, stage 2, and the third stimulation stage, the second perforation area, was shown here. So once again, here is the potential path for 16A. That's our working hypothesis right now. These are colored by, they're sized by their magnitude and colored by time. Each stage of stimulation essentially has its own color scheme. What you'll notice here, I'm not going to get into the explanation of the hows and the whys. It's just be descriptive of what we're seeing here. For stage 1, we see some of the early times happen directly above and then somewhat migrated to the left in this frame. And I'm not going to get with my azimuth. I'm not going to try to say which direction that is. But in the second stage here, our earlier time colored in this pinkish color. As we get later in time, they do seem to move upward. Our third stage, somewhat where we actually had higher viscosity fluid through the perforations, or that was actually injected. And what we can see here, once again, and I'll show it a little better in the next slide, our earlier time events are near the wellbore, and at later time they move further and further away. This is showing the same view, but from above. So it's somewhat, I think we can see some pretty stark differences here. I'm not going to try to explain them. Once again, here is the two well trajectories. For reference, here as well, 5832 in the frame. Our scale here on the bottom is 200 meters. And my Mac mouse, you touch it 2 cents, it moves the slides for me. I'm not going to describe anymore. We actually can see a really good, I would mention that in the third stage, we had the best seismic network coverage. As the team worked through the strings and the various monitoring wells, you can see some pretty good structure coming out into those. Once again, I'm not going to comment. I will let our next presenter, the Peng Zhu and the Itasca team, talk about this to some degree. This is still a work in progress. As a reminder, last time we had this same slide, but a little bit different, and we had some comments on it, is where this essentially the initial estimate for 16B was to have a 500-foot open hole toe. If we look a little bit more closely at these plots here, these are once again in meters. So there's 100 meters, 200 meters, 300 meters up the borehole. So our initial thing at 500 meters essentially put the third stimulation fully behind casing, the second one mixed somewhat behind casing, and the first stimulation would be somewhat mixed in between. That is still under discussion. We want to see how that works out, but essentially, we have to have about 900 feet or a little bit more of open hole to essentially have that third stimulation stage to be essentially interrogatable, not get cemented in. So that's something we're talking about. I can talk about it for right now. The last thing I do want to mention is we talk about trying to do some of those evaluations. Our second presenter today, Samdu Apala and Lynn Monday from the INL, will talk about some of their preliminary models for looking at breakthrough times. Additionally, for some simple cases between 16A and 16B for a single fracture, they'll talk about some more detailed things for a lot of different fracture networks we're looking at. We did simplify these things a lot. These networks I'm showing here are essentially a shortest path. This is prepared by Lita Finella and Golder. The shortest path for a I believe this is 150 meter separation between what would be A on this path and B on this one. The shortest one had 19 fractures. The one with the highest conductance was 96. These are from the stochastic DFN from one of the realizations, but we're just using these to train our models to play and to work for some preliminary estimates as the team does a full evaluation of the seismic data to get a more as much of a deterministic DFN as we can based on the data that we have coming in. It's still a work in progress. We're going to transition over to our next presenter. I'm going to close this off and stop my share and unload my second presentation. If you'll bear with me for one moment while I get the slide up. And I'm going to share the presentation from here, and our presenter is going to be Pengzhu Jing from Itasca. If my system will let me share it, I will get it up for you.
So, can you hear me?
We can hear you. You sound a little bit muffled, but yes, we can hear you. Just let me know when you want me to advance the slides.
Speak louder. Okay. Yeah. So I talked our preliminary comparison between the simulation and the stimulation microseismic stage results. The next slide. So yeah, here as Rob just showed you the field stimulation results here. Is field stimulation results for zone 1, and here I show you 3 different views. So in different, the first one is in the wheel of SHME and SB. Second one is in the SHMAX and SSV, and third one is in SHMAX and SHME. And so the maximum event magnitude in zone 1 is 0.04. Next one. So this slide, so here is our simulation results. So here I also show the microseismic clouds in 3 different views. And in this model, we use permeable and frictional DFN. So in this 600 meter cube, there are roughly like 10,000 mesh fractures. And so they have initial ruptures, they have initial permeable, and their friction angle is 37 degrees. And here are the obtained simulation microseismic results. The next one. So yeah, here I put them together. I put the field stimulation results with the simulation results. So here the color one is the stimulation result, and the gray one is our simulation. So so you can see basically the extent. So the simulation results, the extent of the microseismicity clouds matches with a stimulation. Next one, please. And here is the zone 2. Yeah, so here is the field stimulation events, and the maximum magnitude is negative 0.003 in the 3 different wheels. Next one, please. And here is our simulation results. Again, here is the permeable and frictional DFM. Yeah, I didn't plot the DFM here, but actually there's like thousands, 10,000 of DFM here. Yeah, next one. Yeah, here also put the simulation results together with the stimulation results. And the colored event is field stimulation, and the gray one is simulation. So again, roughly, so the extent of the simulation clouds match with the simulation results. Next one. And here, so here's zone 3. Zone 3 is a little bit different from zone 1, zone 2, because in zone 3, we use the crossing gel, and we think they have a larger viscosity. So from eyes, you can see the extent of the microseismicity in the field is larger than zone 1, zone 2. And next one. And here, so in this slide, so here the simulation results for zone 3. Again, here is the permeable and frictional DFM. But viscosity here in our model, we use 100 poise Newtonian fluid. And also in the simulation, we have a larger extent of the simulation microseismic events, which is similar to our simulation. Next one. Yeah, here I put them together with the simulation results together with stimulation, and again see they match very well with each other. Next one. And here is another, still in zone 3, but in another condition. So in this simulation case, we use initial impermeable and very strong DFM. And here we see also the microseismicity clouds are narrower, and it looks like they are like vanishing frag. And next one. And here again, we compare these microseismicity events. Yeah, they are because this gray is not very obvious, but they go here. So yeah, this extent is roughly match. So yeah, in zone 3, we compare 2 different cases. One is permeable and frictional, and another is impermeable and strong DFM. So from you can see either one will give you a like reasonable match. Next one. So the extent of the simulated microseismic events matches the field simulation results for all the 3 zones. The larger extent of microseismic events, like in model for zone 3 are probably due to the curve simulation of fluid rheology, like Newtonian fluid is 100% point viscosity. And this similar, we use this high viscosity onto measure field fluid used in the simulation. So our next future work, so first we will compare the B value between simulation and simulation. So the B value that roughly is you plot the frequency magnitude distribution and get B value. And we also do the simulation study with different properties, because now we only have two ends of different properties. One is very permeable and weak. Another one is very strong and impermeable. There's some in-between values. We investigate these different cases. And third one, we use we simulate with power of fluid in zone 3. Right now we use just Newtonian fluid with the high viscosity. And then with simulation with further refined DFM, including more deterministic fractures. Here's what I have.
Thanks, Ju. I do see a question came in or a comment from Mark McClure. Mark, if you just want to come off mute and start some discussions, and then we can kind of go from there. And when we wrap up the discussion, this will move on to the 16B work.
Yeah, I mean, thanks for the presentation, Pingju. I think the data looks exactly like a planar hydraulic fracture, and it looks nothing like a complex DFN. For two reasons. First, prior to any of the stimulations, they went to the open hole section and they pressured it up slightly below SH min. A Coulomb analysis would predict that a lot of the natural fractures should be able to slip and stimulate, and nothing happened. Nothing slipped, nothing stimulated. And the reason is that, as we've seen at the EGS Collab project, that having a fracture that's critically oriented for slip is a necessary but far from sufficient condition for slip to occur and then for stimulation to occur. You have to have adequate, first, just conductivity for fluid pressure to get into those fractures. They have to not have cohesion. They have to be big enough to creating. There's all of these things that have to fall into place, and it didn't fall into place. And that's why the injection slightly below SH min did not stimulate the well. So I would encourage you to take your model and try to simulate the part of the data that was prior to the stimulation. And I would predict that the model can't match that data because it's going to predict a bunch of stimulation. And then the other comment is, zone 3, that is perpendicular to SH min. It's a penny-shaped planar feature. That is canonically what a hydraulic fracture looks like. I just don't see why we need to invoke anything to do with a natural fracture to explain that observation.
So I'll have one. Some of these things don't show it that well, Mark, and unfortunately, I don't have the whole slew of images of these things. In the third zone, we actually can see separated by time, and unfortunately, these don't show it that well. But essentially, a number of different clusters of what look like planar features coming in at a number of different angles that do align with some of our fracture sets in the DFN. So you can kind of almost see it here in this vertical section. These orangish ones come here. There's a set that's yellow, and then I'm stretching here because it doesn't look it well. But look at these things over time. We do see some, but look to be at least a number of at least three separate larger scale fractures in the third one. The first two are a little bit less well constrained because we have less data for those as well. But
so the seismic array was lower quality in stages 1 and 2, right? So it's
so it's a little bit harder to make. But I would point out though that there's a lot of additional seismic data that's out there and available to be further processed. So this is a shameless plug for anyone that wants to dive into some of that. And I believe we have, if anyone wants to comment on that further, but there's, I think, a lot more in the catalog that can be further reprocessed or further refined to add more data to these clouds. But for right now, this is what we have to work with. And I don't believe that the Forge team internally is going to do much more work on these, or our partners. So I think if the community wants to look at more seismic data, I think the onus will be on others to do some more processing.
Yeah, I mean, I think this is partly why having a fiber at 16B is going to be so valuable, because oil and gas spent like literally 10, 15 years looking at microseismic like this and thinking it was a complex fracture network. And then fiber came along and it turns out it wasn't. And I think it's a good chance that the same thing happens at Forge. I don't know that, but that's my shameless or fearless prediction. But yeah, I mean, Pingju, have you tried to simulate the part of the data where they injected slightly below SH min, putting fractures into critical stress, but not stimulating them?
So yeah, I tried, but that is long time ago. So not I can revisit that simulation. So you mean the shear simulation before the stage 1, right?
Yeah, before stage 1, they attempted a shear stimulation and it was unsuccessful. There was not shear stimulation.
Yeah, I can look at the data, the field data. Yeah, good suggestion.
Yeah, because I would think that what's happening is you've set up the model so there's tons of shear stimulation, and so the model is going to predict that there was shear stimulation during that period of the injection, but actually there wasn't. And I think that's very important that they tried to do a shear stimulation and there wasn't. The only way to get stimulation and to get microseismicity was to go above SH min, and that means that they had to create hydraulic fractures, and that raises the question of how much shear stimulation actually is happening if you couldn't stimulate without creating hydraulic fractures.
Is there any
Hey, Mark, this is.
Yeah, if
Go
you want
ahead,
to speak,
Branko.
can you like raise your hand or something so I can kind of keep a track so we don't get talking on top of another. I do see Eric Steinhall had a question about, are these isothermal? Yes. These are the short-term stimulation only. So these are isothermal.
Yeah, can I add to that? I think
Yeah, please.
I think seems like I'm getting an echo here. I mean, I'm kind of in the middle between Mark and the DFN one. Yeah, the DFN's a realization, and it's one realization. So you run many, you're going to get different results, right? Because the fracture is going to be different. You're going to have different fractures. And then the other issue is, yeah, the thermal effect we know could have, some of this dilation, aseismic behavior. So to me, it'd be interesting to go along with what Mark says, and you run a uniform case, to see, okay, do you get a hydraulic fracture? If you can match the data with a uniform medium, then it follows what Mark is saying. Now, maybe out further, like these later events, maybe they're intersecting natural fractures, which does make sense at some point that you start intersecting and then the fluid goes off. The other thing is, do you match the pressure history? I mean, that's really important if you're actually capturing the permeability change. Because the shear events and the tensile events should be giving you very different. The tensile events should be giving you very large permeabilities, and the shear events should only be giving you like factor of 3 or 4 or under a factor of 10. Anyways, just some comments.
Thank you.
Hey, Eric, this is Branko from Itasca. I mean, those are good points. This model actually does show propagation for each of these stages, does show some propagation of hydraulic fracture. So it's a combination of two things. So, the model does generate pressure which is greater of SH min. And I agree also with Mark's point that, we should probably go back, and we did model the hydroshearing stage for zone 1. We'll go back and revisit that. However, if you look at carefully the microseismicity for zone 1, you can actually clearly see that the events actually align along plane. So, I mean, it just cannot be just hydraulic fracture. There is actually a combined response, which includes both hydraulic fracturing and some DFN response, particularly for zones 1 and 2. But I would argue that for zone 3, there is more prominent propagation of hydraulic fracture, again, as a result of completion, which is, perforated case completion, and as a result of using cross-linked fluids, which definitely favors hydraulic fracturing.
Yeah, I agree, Bronco, it's possible. I think it's also possible that just the microseismic array was better in stage 3.
Yeah.
And again, I think that's why the fiber is going to be
Well,
helpful.
Well, I wouldn't go and start assuming that data are wrong, So, we
Well,
understand
we know it's lower quality, so I'm not sure it's
I-
wrong. I'm just saying it lowers the confidence in that.
Yeah, there is uncertainty, but I mean, it's too much coincidence that data for zone 1 almost line up with a on a plane, So, I don't know.
But they're not near the open hole where the injection was. So maybe they're relative to each other with the double differencing, they're correct. But it just, to me, that seems too odd how displaced they are or where the injection is. But anyways,
Well,
maybe
that's another reason that, that to me indicates there's probably some DFN effect. So.
Other questions from anyone else in the audience? Okay, I'm going to move on to Sam and to Lynn. I'm going to stop my share. You're going to share your own slides, Sam?
Yeah, I can do that. 1 second. Can you all see them?
Yes.
Okay, great. So Lynn and I are gonna discuss some work that we've been doing very recently related to the sensitivity analysis of well 16B options. 1 second. Let me open my laser pointer. Yeah. And Lynn is gonna set up the background and context for this talk. Lynn, can you take it over?
Yeah, so this is eventually this will be the more of the setup that we use, where we have this more complicated DFN that Alita has given us from Golder, and we'll look at the maybe a short-term simulation to make sure that the wells are connected, and we'll look at maybe a 200-meter block of the DFN network to look at look at connectivity, look at the number of places. If we have a single injection point, how many fractures the production well should intersect, and in what regions. Then we could have like intermediate term simulations we plan to do, which is kind of what Sam's going to look at next or present next, which would be looking at permeability, trying to determine what the permeability is, what the fracture network might look like based on the tracer flow between the two wells. And then longer term, we could look at performance. And so to do that, we've started doing some sensitivity analysis just on distance and permeability. And then we can, another one that we will do later will be the fracture network. So you can,
Yeah.
take over now.
Thank you, Lynn. Thank you.
Yeah.
So following on what Lynn said, while we were waiting for the more complex DFN model on which to perform the sensitivity simulations on, we took a single fracture model, and the fracture model with the matrix is shown towards the left-hand side. Both these fracture and matrix are solved in a loosely coupled scheme using the Moose's multi-app system. On the right-hand side figure, we show only the fracture model. The black dot is the injection point, and this is fixed. And the green dot is the production point, and we varied the production point. We picked like a distance of 25 meters to 125 meters. And we also varied some model parameters such as the flow rate and the permeability. So
I'll mention the models, like a thermal hydraulic model. We have an equation of state for the fluid, and we have a fixed permeability. It's not a function of the pressure or the aperture or anything. And we're solving these together as a single simulation that's fully coupled. Not the multi-app stuff yet. So they are conformally matched, and we get good heat transfer between the matrix and the fracture. Yeah, that's all, Sam.
yeah, thanks, Lynn. This slide basically shows us the temperature profile evolution with the days. Again, the black dot is the injection location, and the green dot is the production location. And as we see that as time passes, the production location tends to reach a steady state temperature. We're only showing until 5 days, but the plot on the bottom, which shows the temperature output with respect to time, indicates that as time is increasing, the production location will reach a steady state temperature. In a similar fashion, this slide shows the tracer mass fraction profile evolution with the number of days, similar to how the temperature profile looked. As the number of days has been increasing, we see that the production location is reaching a tracer mass fraction of a unity value, and this can also clearly be seen in the plot on the bottom. One thing to probably note here is that the time until which the temperature reaches a steady state is kind of lagged behind the tracer profile, and we can clearly see that in the comparison on the figures on the left-hand side, where the top two figures show the temperature evolution between 1 and 5 days, and the bottom two figures show the tracer mass fraction evolution between 1 and 5 days. And we can see at the production location that the temperature is kind of a little bit lagged behind the tracer mass fraction for a certain permeability and flow rate settings. So based on this,
Hey, Salim, another thing I can mention is that initially we assumed the fracture is completely filled with fluid at 470 degrees, and we're pumping in the cold tracer fluid. So initially it's 0 and it goes up to 1. And
yeah, that's right.
Okay.
Thanks, Lynn.
Yeah.
So based on that observation, we want to optimize the well placements, and we had to start somewhere. So we define our objective function for optimization in the following manner. The objective function is basically, as shown in this plot, the time difference between when the tracer mass fraction reaches a value of 0.5 and when the temperature reaches a value that is between the maximum and minimum temperatures. So the tracer mass fraction plot is towards the left-hand side axis, and the temperature plot is on the right-hand side axis, and the x-axis is the time in days. So the time difference between these two breakthroughs is what we considered as our objective function for these sensitivity simulations. So now we kind of discussed some sensitivity analysis that we performed on the single fracture model. For a fixed value of permeability and flow rate, the left-hand side figure shows the temperature evolution with time as a function of the separation distance between the injection location and the production locations. And the right-hand side plot shows the same thing, but for the tracer mass fraction, not the temperature. And one thing we can clearly observe is that as separation distance increases, we see that the temperature evolution with time is much more gradual compared to smaller separation distances, and that makes physical sense. And this is also mostly true with respect to the tracer mass fraction as well. As the separation distance increases, the tracer mass fraction reaches a steady state in a delayed fashion, except for this one plot here. Rob just pointed out before the presentation that this one plot is looking weird. It might have been a mistake on what CSV file I grabbed while post-processing the results. So I will look at it again, but we expect that at 125 meters distance, separation distance, this tracer mass fraction will be more delayed compared to the other distances in terms of it reaching saturation. And this slide shows how both the temperature evolution and the tracer evolution depend on parameters such as the permeability and flow rate as a function of the separation distance. On the top, there are two plots which are shown for a permeability value of 2e minus 13 and a flow rate of around 6 kilograms per second. The bottom two plots show the same temperature and tracer evolutions for permeability of 5e-12 and a higher flow rate of 8.6 kilograms per second, we can see that there is definitely an influence of the permeability and flow rate on the temperature evolutions. Although it's kind of less clear in this particular slide, there is definitely an influence of these two parameters on how the temperature evolves with time and how the tracer evolves with time. But I think this slide kind of summarizes that influence in a more objective fashion, because we computed our objective function, which was the time difference, which I described in one of our previous slides. And the top two plots show the objective function on the y-axis with respect to the flow rate and the permeability, considering a separation distance of 25 meters. And the bottom two plots show the same thing, but considering a separation distance of 75 meters. So one clear thing that we can observe here is that the time difference has a deterministic relationship with the flow rate, but the permeability seems to not affect this time difference because the time difference values for different permeabilities seem to be quite random. So that's one of our observations here, and it kind of makes physical sense as well. So once we finish this sensitivity simulations, we recently got a more complex DFN model to consider from our partners at Golder Associates. So this discrete fraction network model has a mesh size of 2 meters, and it has around 300,000 total nodes. So, because when we consider, production locations, the line of production can intersect with multiple nodes on the fracture planes. So in this process, we have also developed an algorithm that kind of automatically determines where this line of production intersects with multiple locations in the DFN model. And we will couple this new algorithm that we implemented in Falcon with the new model that our partners have given, and redo the sensitivity simulations considering different permeability and separation distances and also flow rate values. That is our plan for the near future. And obviously, we will also consider the matrix with the DFN simulations. This matrix and DFN are loosely coupled, and the heat transfer is achieved using point sources. And one nice feature about this matrix is that we can do some automatic mesh refinement wherever the matrix intersects or is close to the DFN model, as you can see from the figure here. The mesh near the DFN model is much more refined compared to the other matrix regions, and that could save us some computational time while giving us accurate results. So that is what we're trying to progress towards in the next few weeks. So to summarize, we are performing some sensitivity analysis to investigate the influence of separation distance, flow rate, and permeability on the time differences, which we defined as our objective function. We tried these sensitivity simulations on a single fraction network model, and now we are moving on towards multiple fracture network models. We will work with the reservoir team and Itasca and Boulder to down select a few scenarios in the future for which we will run the full physics simulations based upon our sensitivity simulations on the DFN models that we described earlier. With that, that concludes our presentation for today. I will be happy to take questions.
Okay, just a few things for commentary before we take questions is, the purpose of a lot of these things, we have to serve multiple purposes with this first production well 16V. So, we need to be able to characterize the fractures that we created, which might go to answer some of the questions that we discussed for the stimulation. So we calculate or characterize the fracture zones that we created, either single fracture or multiples, characterize the hydraulic parameters of those. Then we also have to serve, the purpose of like confirming connection, and then doing some shorter term tests and longer term heat extraction. So we're trying to optimize the distance between 16A and 16B so we can be as flexible as possible. And so we start out with these simple cases to try to get it started on there, which will be our earliest probably breakthroughs, and then get more complex as we go once we settle into a few more promising cases, then we'll go to full physics simulations that have pore elasticity, thermal elasticity, reactive geochemistry to start planning out not only these initial flow tests, but also longer term extraction. So with that, I'll open it up to questions from the field. I see Peter Meyer, you did have a question. If you want to elaborate on that, I just answered you very briefly in the chat, but if you'd like to elaborate, please do. Anyone else?
Yeah, I was just curious how you do the heat transfer across, like what's the surface area or what's the fracture porosity? Is it just like an open aperture and then the heat transfer area is the area of the fracture? Is there more sort of rough?
So for the cases that,
curious.
okay, so for the case that Sam showed, essentially, yeah, that fracture is, it is essentially one contiguous mesh. So it's a 2D plane, essentially a 2D domain mapped into a 3D volume that they share nodes between the two domains. So it's essentially two matrix blocks or two blocks in there. And that fracture is simulated. Essentially, you're still using an equivalent porous medium type approach. Very high porosity, fairly high permeability. Surface areas are directly, across the faces. The models share that area of the faces. So that's for that one. For the more complex ones, it gets a little bit a little more challenging because it's really, I'd say, a big challenge to model essentially a contiguous mesh or a single mesh between those two zones. So then we actually do an on the fly, we'll solve the fracture domain and then calculate the surface areas, differences for heat flux and mass transfer between the two domains, move the amount of fluid either in or out of the fractures, and then continue on the next time step with a Picard iteration.
Yeah, it's a tricky problem when you're crossing all these elements.
It is, especially when there's a whole bunch of fractures that are close together. It gets real tricky, especially depending on the resolution of the matrix mesh and the fracture mesh. So that's one of the things that we're challenged with right now. And I've struggled for years to try to find a way to do this really clean with all within a single mesh. But just especially when you try to start doing mechanics on there, your mesh quality for the matrix in between the fractures can be really bad. You get bad aspect ratios, and your mechanics essentially just they're just horrible. You get horrible, convergence if they converge at all. So it's a challenge for sure. It's something we're still working on.
Yeah, we always need more elements.
Which means more time steps. Your Grant numbers and your Peckley numbers just get real challenging. So it's a fun problem to work on, though. I'm really excited with with that line sampler they came up with that can you just shoot a ray for what the well would be through any fracture domain, and it'll pick up anywhere the well would intersect. Then we could put a sync term at those intersections so we could look at pretty complex flow paths at least coming out or going in. So that'll be pretty interesting. I believe we'll have some pretty detailed presentation of this at GRC in next month or later this month.
Great, thanks.
Other questions, comments? So in the near term, what we plan to do with a lot of these things is we will do, once we get into more of the full physics, but we will be planning essentially writing an interwell flow test plan. That plan will incorporate things like how we do testing of the 3 fracture zones the 3 stimulated zones. It will include some longer term tests, instrumentation, flow rates, monitoring points, monitoring types of data. And once we get some of these things drafted, this is meant to be a community-driven experiment plan. So we will be sharing this and getting input and working with the community to help put this plan together. I'll probably start drafting at least at a high level an outline in the next month. So be look out for that, and we'll glad to take any input we can get for these things as we move forward. So if there's no further questions, I just see a question come in. McCool, just want to go ahead, McCool. Just ask your question.
Okay, I was just going to ask, and maybe I missed this. I'm sorry if I did. Is the fracture modeled as a discrete crack with a finite width, or is it part of the matrix grid blocks with a higher permeability and porosity?
Oh, well, it's modeled as a 2D plane in 3D space, basically.
Yes, but is that plane a part of the matrix in terms of how you grid it? Is it just a high permeability, high porosity grid block in the
No, it's well, okay, so for this example, we're doing like, we solve the fracture by itself as what Psalm said, a 2D plane in 3D space, and then we transfer point heat sources to the matrix, which is the gray block in the background. So, and then solve that, and then transfer heat sources back to the fracture, solve it again. So that's how this one is solved. But the other simulation Psalm showed previously with just the ellipse, we can mesh that one contiguously and just solve it together. So it's just the fracture is just a 2D fracture with some permeability that I guess should account for the aperture. And Rob, is this correct?
It is correct, but I
it's
think
surrounded by coupled to the matrix, which is in 3D.
so. Cool, I know what you're getting at, and so what you're looking at here is these are essentially reduced order, lower physics, lower fidelity models. These fractures won't grow; they're just simply conduits for fluid flow. Once we get, later on, we do intend to look at, we could actually have these fractures more active, looking at things either XFEM or essentially like, maybe an IPG formulation, or, we're looking at some cohesive zone modeling for damage, or also a phase field. So we're still looking towards some of those. For right now, we're just trying to keep it simple, because then we add more physics to these things, the computational time becomes somewhat intense. And so we're trying to get some quick answers for right now to help inform the planning. We start doing planning for the location, and once we worry about more of the actual tests and what we'll see in the field when we start moving fluid through them, then we'll actually do some more full physics models where there could be, essentially crack growth, crack movement, and such in the model. Does that answer your question?
Yeah, and really my primary concern and my suggestion was going to be that, if you do this model as a crack with a finite width, then you can also compute the strain and the stresses and the geomechanical part of it, which allows you then to look at things like microseismicity and so on. And I was just wondering if that's possible from this model, is to actually compute the stresses and strains on the other planes, and then be able to look at slip events and microseismicity and so forth. Is that doable in this framework, or is that a separate field?
It's doable with the framework. Some of those things you mentioned aren't fully implemented for simple cases. So especially, like we could do contact mechanics, and we could actually have these two things separated, but the burden of that is it's a real challenge. We can, I think even one of our opening slides, or one of the things they do for the promos, do show where we do some models and things as separate cracks, where we're throwing some thermal stimulation where the cooling front is like essentially opening the fracture. So yes, we can do that. It's just a matter of how we implement. I think the most promising way, we're just finish up the work right now, is the IPG. We're doing a mix between continuous and discontinuous Gilherkin with the penalty method, or the interior penalty. That seems to be a really, really promising way to actually essentially have those things open up. Where right now is with the flow, once we move away from having a 2D plane that's contiguously meshed, then we have to sort about solving that fluid flow in that crack as it opens. And so that's a little bit more of a challenge to solve inside the crack if we have it actually, moving explicitly. And so we're looking at things like even just maybe it has a lubrication type equation to solve in there to be a little less cumbersome. But that's still a little bit in the works for right now.
Great. Well, thank you very much.
Oh, my pleasure. Other questions?
And yeah, Rob, I mean, I just reiterate what I said earlier, if propagation of newly forming hydraulic fractures is a critical or a dominant process here, and this is a model that does not have that, then it raises the question, is this representative of what's actually happening?
Yeah, so I didn't point out, but these complex examples actually take the output from Itasca's models, where they're essentially the hydraulic crack, or the hydraulic fractures were actually already in here. So they were created and handed off from Itasca, and we're just moving fluid through the ones that were already. So
hey, thanks for clarifying. Okay.
No problem. We might be getting off early today. And if that's the case, I'll thank everyone for their attendance. Once again, if there's questions or comments that anyone would like to share, but they don't want to share with the group, I'm happy to take questions, comments, or even snide remarks privately. Just email me, and we'll go from there. Our goal here with all these things is to, get community input and make for the best possible experiments in the best possible foresight. So I thank you for your attendance today. And I will be looking probably to some folks that are in the audience today to be some of my presenters for future meetings. So thank you, everyone. Have a great rest of your day, and we'll talk again soon.